time. The next talk is by Sam Derbyshire, and the title is A New Interface for GHC Typechecker Plugins and Typefamily Rewriting.
Right. So let's get started. So I've been working with Richard over the summer on GHC, and one of the things I've been doing is working on these type checking plugins, and in particular rewriting type families. So I'm going to go over that. So first I'll talk about kind of what are the things we want to do in these type checking plugins. I'm going to review what we have currently, talk about what I'm adding, so these rewriting of type family applications. And then I'm going to give a quick example so we can see some actual code, but it'll be quite short, but I'll link to the full code. And finally, I'll talk about this new library I've written. This should make life a lot easier for authors of type checking plugins. So first off, what would we be using a type checking plugin for? So I assume a lot of people already know you can use it to solve instances and rewrite type families in a kind of not depending on GHC's own logic. So here we're going to focus mostly on the type family aspect. And I have some basic examples to show. So first off is a bit of arithmetic. So if we have a type family like this, where we're just basically inductively defining addition, we quickly run into some problems reducing this type family application, because the way this works is we're looking at the first argument. So the type family will be able to reduce only when we know what the first argument is. So that can cause some issues quite quickly. So for instance, here's something that the GHC can't solve. So n plus suc n equals suc of n plus n. And the problem here is the first argument to this addition type family, the first argument is a type variable. So we don't know, well, is it 0 or is it the successor of something? And so because we don't know, GHC just doesn't reduce this type family application. It stays like this, it stays stuck. And as a result, it's not able to reason about it. So that's one thing we'd be able to do with a plugin. So for instance, Christian has the type not normalized plugin, which introduces logic to handle this. A second example would be row types. So a row type is kind of the type level logic that we would have to handle some like extensible records. So we'd have something like field 1 is of type int, field 2 is of type bool. But the important thing is with these records, we want to deal with unordered records, so that the order in which these fields are specified shouldn't matter. So if we imagine trying to set this up with a type family, we need an equation like this. So we have a row R, some abstract set of fields and types that is not determined yet, and we'd want to be adding 2 extra fields to it. So we add the type W with name L and the type V with name K. And one thing we might need to prove is that we've got an inequality like this. So we'd be reordering this type family application. But the problem with that is in GHC, we can't have a type family equation where the left-hand side is also a type family application. And so here's the error message we'd get from trying that. Illegal type synonym family application in instance. And well, there are several reasons for this, but one of the reasons is non-confluence. So here's a very simple example. We've got a type family F, and we suppose we're allowed to have it refer to this type family F in an argument. So we have these 3 equations like this. And now we can see if we take a type like f of bool, well, we could reduce this in 2 ways. We could start by reducing the outer type family application. So we use the first equation there, f of bool. So we got a equals bool, and that gives us bool. So that's if we reduce the outermost type family application first. if instead we decide to reduce the inner type family application, so we start by rewriting fbool, well, fbool reduces to float. So, and we've still got the outer f, so we get f of float. And then the equation that would match here would be the third one. And then we get maybe float. So this is just a simple example to show that if GHC just allowed type family applications on the left-hand side, in a naive way at least, like this, then the order in which we write type family applications would end up mattering, and we could end up with different results. So that's one of the reasons why GHC doesn't allow that. But in plugins, we will be able to do that. So it's kind of becomes the responsibility of the plugin author to write code that reduces type family applications in a way that, I mean, that prevents this non-confluence problem. I mean, if a plugin author wants non-confluence, they can have it, but I think generally speaking, it's something we'd want to avoid. So let's review now a bit these type checking plugins. So first, how do they fit in with GHC? So we can imagine we've got GHC's type checker on the left here. So we've done the previous stages, like we've passed, we've renamed, etc., and then we start type checking. And then when we're about to start type checking, we initialize the plugins. So that calls this, for each of these TC plugins, they'll have a function called init, which I'll review in a second, that kind of starts up the plugin, and it can do things like start up some external tool like an SMT solver or something like that. And that will generate some kind of plugin environment S, which the plugin author can choose. And that gets passed to the other stages of a plugin, which are the solve stage and the stop stage. But it doesn't call them, it just passes this data that they're going to need. And then it's when we're in this type checking loop that we actually call these plugins. And for solver plugins, there's two ways they can get called. They can get called to simplify some given constraints, or they can get called to solve some wanted constraints. So this will keep happening in a loop until GHC decides it's done, it's solved everything, or it's finding things that are definitely insoluble. And then it'll finish and call the stop function. So that's kind of what we had already. And now let's see what we're adding. So this is this TC plugin data type, which had these three things we saw previously: init, solve, and stop. And we're adding a new field, which is rewrite. So rewrite, it takes in this plugin state. We'll see a bit more what plugin state is if you're not familiar, like how it's used in practice. And then it returns a map. So this just means a map from tycon, which is like going to be the name of the type family we want to rewrite, to a rewriting function. And what's a rewriting function? So we want to write a type family application. So we have the type family name here. We're going to have its arguments, however many arguments, just to make sure the type family application is exactly saturated. And we also specified the given constraints at the point of rewriting the type family. So that's knowledge we already know at the moment we're rewriting, which, as you'll see in an example, we need to know sometimes. And we return this TC plugin rewrite result, which is basically just a maybe type. So either we don't do anything, or we rewrite. And if we rewrite, we have to specify what type we rewrite to, but also specify a coercion. In the plugins, it doesn't really matter. We can use some type of universal coercion, like believe me, which is kind of what we already did for constraint solving plugins when we were solving inequalities. And the other thing we're allowed to do also is emit some new constraints when we rewrite. So that's kind of quite different from how GHC usually worked, because when GHC reworked type families, usually it never created any new constraints. But in a type checking plugin, we're allowed to do that. So in terms of the previous diagram, we're just adding one new stage. And as I explained previously, we get past these given constraints from the type checker, and we get past the arguments for the type family application, and we have to specify a reduction, which is this pair of a type we reduce to and a coercion that witnesses this reduction. Okay, so now I'm going to go over one of my own examples. And this was inspired by a little challenge that Stephanie Wyrick posed about a year ago, which is to implement a strongly typed version of SystemF. So this would be some kind of AST. We'd have some terms, but it would be a gadget. So we keep additional information at the type level. So in this case, it would be a context and a type. So for example, we could have function application. So that takes a term in context phi, which is a function type, A to B, and then a term in the same context phi of type A, and applies that function. So we'd get a term in the context phi of type B. The other thing we have, so in SystemF, compared to lambda calculus, is we have these type lambdas and type applications. So for instance, we could have a for all type, and instead of applying it to a term, we apply it to a type. So this would be a singleton for a type, and then we apply it, and we have to substitute in the type in the term. So for instance, it might be the identity type, like for all x, x to x, and we apply it to int, and we get int to int. And so the key thing here is this substitution type family we've got. So let me just quickly show what that looks like. So we have some apply sub type family, which would take a substitution. That's in the example I've got, it's some declarative type. So it could be the identity substitution. It could be a composition of substitutions. It could be, well, as in the example below, we extend the identity substitution with just a type. And so we've got this type family, and we'll see what we want to prove about this that we can't prove normally. I'll quickly, for later, we'll see that it's important when we're writing type checking plugins to take into account the visible but also the invisible arguments. So the full kind signature of this would be, so it takes a substitution and a type and returns another type, but it takes in some additional invisible arguments, so contexts and the kind. You don't need to worry too much about what this is, but it's important to know that it takes in 3 additional arguments. So when we're writing this type family in a plugin, we have to take into account these additional arguments. That's the same as it's been in the past in type checking plugins. So what difficulty do we have with the setup, and why would we need a type checking plugin? It's what we've seen before, problem of rewriting an argument which is a type family application. So we want to rule like this. So we're applying a substitution T to A, and then we apply the substitution to S to the result of that substitution. And we'd like to rewrite this to applying the composite substitution S composed with T to A. And there's several reasons for that. One of the reasons is then we can completely reason in terms of this language of substitutions we've got, and we'll have many kind of propositions on substitution that we can rewrite. We can rewrite the composite of the identity with something. Well, we can just remove the identity and things like that. Or we could, if you've got 3 compositions, then we want to reassociate so that, if it's A composed with B composed with C, the parentheses on one side or the other, then we want to be able to reassociate. So we're going to need a type checking plugin to handle this type family in a type family argument. And the other thing is we might also need to use given constraints. So we might have something like apply sub S to F, and the given saying that F is equal to apply sub TA. So it might not be immediately obvious. We might need to use a given constraint. And this happens, on GHC 9.0, for instance, it happens quite a lot because we have flattening of type families. So we'd often see things like this. So we need to be able to handle that situation also. So that's kind of why we had the given constraints passed on to these type family rewriting. So let's see what this looks like if we try to implement a type checking plugin to rewrite this type family. so we have to specify a rewrite function. That's what we saw before. And so this plugin def is the little S we had in the diagram. And for people who are familiar with type checking plugins, we looked up a lot of information like what is the name of things. So here in particular, we'll have looked up the apply sub type family. We have looked up its tycon, so we can refer to it in the plugin. And so we have to specify a map for each type family name, a rewriting function. So here we'll have the apply sub type family, and we'll have the rewriting function associated to it. And we can specify this as a list and use the list to UFM function in GHC to get a unique FM. And so then this rewrite function, well, so it takes in these definitions because I passed them here, takes in the given constraints, it takes in the arguments to this apply subtype family, and it's going to be a fully saturated application, and it's going to have to return a rewrite result. And so in this case, we have 5 arguments. If you recall, I had the full standard unkind signature for the write sub for the apply sub type family, which had these 3 extra invisible arguments. So we have to take those into account. So I won't write out the full definition of this function because it handles a lot of different cases, but that's going to be available in the repository. But for example, if we were in a situation where we've got these arguments and we've got another given like this, so this argument here to the substitution is another application of apply sub, so that's going to be the nested type family example, then we'd rewrite something like this. We'd say, well, so this is apply sub of t to, apply sub to this. So then we compose them. So here we'd create a tycon application of this composed data constructor, promoted data constructor. When we pass all these arguments, so we'd have the first substitution here, and then the inner substitution here that we've obtained from a given constraint. That we're not emitting any new constraints. We don't need to do that here. And then we can, so this is just the type we want to rewrite to, and then we can specify it as a reduction. So in this case, this is specifying a nominal reduction, and it's specifying this kind of string here. You can specify whatever data you want. This is the usual thing you can do in type checking plugins of specifying a universal coercion. So that's a little overview of how we would rewrite a type family with this new interface. To finish up, I'd like to talk about the new library I've written that kind of simplifies all the things around writing type checking plugins. So one of the problems with writing type checking plugins is we have access to way too much stuff. We have access to pretty much the whole of the GHC compiler. And that means we have to know exactly which function to use and where to import it from. And this leads to import lists to look like this. So just absolutely loads of things, and things have changed across GHC versions, which means it's quite hard to maintain. Loads of CPP instructions. It's just a nightmare. So instead, my idea was, well, let's have a library handle all of this. So we can write a library that exports something that tries to be as stable as possible, and in particular will handle these internal GHC changes and just export what an author of a type checking plugin would need. So we replace this by just import a single module. And this is quite helpful to get started for beginners, because now we don't need to go looking to see where is everything defined. So for instance, we could just import a single module and then say we want to turn a coercion into an evidence term for inequality constraint. Well, we say we don't remember which function that is, so we just put an underscore and use typetools, and we get a suggestion: use ev coercion. Or another example, where we want to apply a type family or promoted data constructor some arguments. How do we do that? Not sure. Put a type hole, make typecon up. So, I mean, obviously in practice, it's not going to be as simple as this, but it helps so that we don't have to, because otherwise, if we didn't know which module to import it from, we'd never be able to get these suggestions. So it's quite helpful. And the other thing is, I think the package documentation can be quite helpful. So I've written loads of like small snippets to get people started, to orient people, because there's a lot of things one needs to handle when writing a type checking plugin. So for instance, looking up all the names when we start a type checking plugin, that's not obvious, and it's not necessarily very well explained. So the package documentation is kind of a way to get people started and to tell people how to, or what things they might need to do, like enable call-int or enable dump tctrace and how to look through tctrace and things like that. And there's a few helper things that I've also added to the library. So for instance, emitting custom type errors, that's always been kind of annoying, because you need to look up all the constructors for this error message data kind, and then construct a type for this error message and everything. So the library kind of handles that.
I think we have to come.
Okay, one last slide.
And
yeah.
If you want to have any questions, you have to.
Yeah.
And now.
Yeah. So we've got an API for custom type errors, which simplifies things a lot. So this is all available now. So the library is available in Hackage. Everyone can use it. The Typefamily rewriting functionality, so that's been added natively to GHC 9.4, but it's also already usable on GHC 9.0, 9.2 if you use the package. It's going to be slightly less efficient because it has to use the existing API, but it still works. And then the GitHub repository contains the full example for this SystemF, and the slides available online. And finally, I've got a blog post in the works on the Twig blog, which will do a more in-depth overview of constraint solving and type checking plugins. So for all the necessary background, if you're really beginning writing a type checking plugin, and that's it. So
okay, thank you, Sam. This looks great. Thank you. I'll ask two questions, even though we're a bit over time. So first is by Adam Gundry. Do you have an example to motivate typefamily reductions emitting new wanted constraints? It seems fishy to me, as we don't have a clear specification of when a typefamily gets reduced.
Yes, well, I don't have so many motivations. One of the ones is that's the mechanism I'm using currently to emit new type errors. So if you want to emit a type error as you write a type family, you can do that by emitting a type error constraint. Or, if we change to Adam's unsatisfiable constraints, we could emit an unsatisfiable constraint. But the idea was also to experiment. So it wasn't difficult to add this functionality. So I thought, well, let's add it and see if people find uses for it.
Okay. And one question by Joachim Breitner. What core gets emitted for these reductions? Essentially unsafe cores, right? Can plugins opt into producing evidence for the rewrites when possible?
So this is the same as normal type checking plugins. So you can pass any coercion you want, really. But the thing that pretty much all plugins always do is just say, use a universal coercion with plugin provenance, which, as Joachim says, is basically unsafe coerce.
So the answer to being able to opt in is essentially yes, nevertheless. I mean, plugins
yes, but there's not really in my opinion, a good framework for, there's not a custom programmable language of coercion. There's not an extensible language of coercions that you could use. You have to use the existing coercions that exist in GHC, and you can't use the typefamily rewriting coercions because, well, specifically those are too specific. They don't handle like rewriting type families with type family arguments and things like that.
Okay. All right. We have to stop here. Thank you very much again, Sam.
Thanks.
Then the next speaker or the next